Hello, this is MAT221. This is Mrs. Johnson. This is our next video on applications to the derivative, section 4.1, dealing with related rates. From the worksheet that is in the Blackboard folder, this is example 5. It says a water tank has the shape of an inverted circular cone with a base radius of 2 meters and a height of 4 meters. If the water is being pumped into the tank at a rate of 2 meters cubed per minute, find the rate at which the water level is rising when the water is 3 meters deep. The volume of the circular cone with a radius of r and a height h is given by this formula. All right, so this is a more complicated formula. First of all, how do we know it's related rates? We know that this is a related rates problem because of the fact that we're given here. You can see that we have rates of change. Here's our derivative. We can see a rate of change, and we're asked to find a rate of change. Notice what is the rate at which the water level is rising, so they're asked to find a rate of change. So let's look at let's decipher this problem piece by piece. First, it says we have a base radius of 2 meters and a height of 4 meters. So what that is the actual cone. So the cone itself has a base radius of 2 and a height of 4. Now I'm labeling these with numbers because the actual base of the cone and height of the cone do not change. That's the given tank shape, and that does not change. However, you can see that the shape of the water in the tank is changing, but the actual tank itself is not changing. So notice we're labeling those with numbers or constants. Next, it says that the water is being pumped into the tank at a rate of 2 meters cubed per minute. That means water is going into this tank, changing what? Changing the volume of the water. So really what they're giving us here is that the volume of the water is changing by 2 meters cubed per minute. That's a dV dt. All right, what else do they give me, or what else do they ask me here? They're asking what is the rate at which the water level is rising when the water is 3 meters deep. Well, the water is changing. So if we look at this water right here, the radius of the water is changing. So I'm going to label that with an R. Notice, unlike the last problem when we talked about a tank that was cylindrical, a cylindrical tank, the radius would stay the same throughout. But here, the radius of the water is actually changing, and as is the height of the water, which I'm going to also label with a variable. Now, they told me the water at this point is 3 meters deep. Well, what is that? That is the height of the water in the tank, but I can't label the H with 3 just yet because that height is changing. It's a variable, so I have to label it with a variable. But I know at this particular point in time, the height of the water is going to be 3 meters. And they're asking me to find the rate at which the water level is rising. So they're asking me to find the rate of change in the height of the water, which is dH dt. They're asking me to find dH dt when, at the point when the water is 3 meters deep. So they gave us the formula that relates the volume and the height. But the radius is also involved here. So if I wanted to take the derivative with respect to time of the volume equation, I actually don't have enough information about the radius r or the rate of change of the radius dr dt. So in this particular case, when we don't have enough information to move forward by taking the derivative implicitly here with all 3 variables v, r, and h, we have to look somewhere else to find a relationship between the variables so I can change the volume equation here to just be in terms of h and v, because that's all the information they gave me. They gave information about dV, they gave me information about h, and I want to find dH dt. So I look at what I have here, and I look at this particular point in time. If you looked at this triangles, it actually would be two triangles that would actually be similar triangles. Notice there's a large triangle here where the radius or the base of the triangle is 2 and the side of the triangle is 4. And then there's a little similar triangle, remember similar triangles from geometry class, a little triangle inside there where the radius or base of that triangle is labeled with R and the height of that triangle is H. And then I would use my properties of similar triangles that we learned way back in geometry class. We know that similar triangles, two triangles that are similar to each other but not congruent, their sides are in proportion. So I know that the radius to the height is equal to 2 to 4, or the radius to the height ratio. So if I did base is to height as base is to height, I'm doing what's called the ratio of their sides. So I know the ratio of the radius to the height is equal to 1/2. Now I'm going to solve for R here just by doing a little bit of algebra. So I'm going to cross multiply there and say R is equal to 1/2 H. Now what I'm going to do is, now that I have a relationship between R and H, I'm going to substitute that value into my volume equation. So when I take my volume equation, I'm substituting R as being a relationship of 1/2 the height. And I'm doing that substitution there. Then I'm going to just do a little bit of algebra to clean up the equation. 1/2 squared is 1/4. 1/4 times 1/3 is 1/12 times pi. H squared times H is equal to H to the third. Now I have a volume equation that represents this cone in this instance in terms of just the height of the cone. Now let's take the derivative of this expression with respect to time. Now that I have two, and we're going to do this implicitly. When I do that, I get dv dt on this side equals, the 3 comes to the front, keeping these constants of 1/12 and pi, so I get 3/12 pi. H, subtract 1 from the exponent, becomes h squared, times the derivative of the inside function, which is dH dt. And again, just cleaning this up, 3/12 is equal to 1/4. Now I have an expression of the rate of change in the velocity in terms of the rate of change of the height of the water. Now what do I know here? I know that dv dt is 2 meters cubed per minute, and at this particular point in time, the height of the water is 3 meters. Notice I don't put these numbers into the expression until after I've taken the derivative implicitly. Once I do, I get this expression, and I can now solve for dH dt. Solving for dH dt, I get dH dt is equal to 8/9 pi meters per minute. Now you could change this to a decimal if you would prefer. I left it here in exact form, so it's in terms of pi. So the rate at which the water level is rising when the water is 3 meters deep is 8/9 pi meters per minute. Let's look at the last example in the packet. Example 6 says a baseball diamond has the shape of a square with sides 90 feet long. Tweety is just flying around the bases, running from second base, top of the diamond, to third base, which is the left side of the diamond, at the speed of 28 feet per second. When Tweety is 30 feet from third base, at what rate is Tweety's distance from home plate, the bottom of the diamond, changing? All right, let's go through what we have. The sides of the diamond are 90 feet long. Tweety is flying from second base to third base in this direction, but his distance between second base and third base is changing. So I'm labeling this with a variable. So from this, I get dx dt is equal to negative 28 feet per second. Now, why is this negative? Because look at the diagram. We know x is getting smaller, so that means our derivative must be negative. He is 30 feet from third base. So at this particular point, x is equal to 30 feet, but we can't label it yet until after we find a formula and find a derivative because x is changing. They're asking me at what rate is Tweety's distance from home plate changing. Well, the distance from home plate, we don't know. We'll call that z. So they're asking me, what is dz dt? What is the rate of change of the distance from home plate? What is that rate of change? So next, how can we relate x and z? Well, again, looking at the different things that we use to relate rates, one of the most common is if I have sides of a right triangle, I could use the Pythagorean Theorem. X squared plus 90 squared will equal z squared. And I only have two variables here. I have information about x, and I want information about z. So I can simply take the derivative implicitly with respect to time. Doing so, I get 2x dx dt plus 0, because remember 90 squared is a number, equals 2z dz dt, which is the derivative implicitly of z. Let's see at this point now, what do we have? I need a value of x, which I have, a value of dx dt, which I also have, a value of z, which I do not have, and I need a value of dz. I want to solve for dz dt. So in order to find this, to find dz dt, I have to get a value of z at this particular point in time. Now it wasn't given to me, but I can find it. At this particular point in time, we know that x is equal to 30. I know that this side of the triangle is equal to 90, and this side would equal z. So at this particular point in time, I can use the Pythagorean Theorem to get my value for z. Now we plug this into the equation, and I get 2 times 30 times negative 28 feet per second equals 2 times 30 radical 10 times dz dt. Again, this is just algebraically and numerically solving for dz dt. I get negative 8.8544 feet per second, meaning that the distance between home plate and Tweety is also getting smaller. As you can tell, this is a hypotenuse of the triangle, and the hypotenuse is getting closer and closer this way to 90, but it would be bigger than 90 at any given point. This is my answer to the question that they asked me to. What is the rate of change between Tweety's distance from home plate? All right, so this completes this worksheet on related rates. I know these are difficult problems. You might have to go back through these videos several times again to look at what we've done here. There's also several other worksheets in the worksheets folder in these Unit 4 worksheets that you could look at to work on more problems for related rates. There should also be answer sheets in those folders also. And also, please feel free to email me any questions you have as you struggle through these questions. Have a great day.